Welcome to this lesson on optical isomerism. In this topic, we'll learn what optical isomers are, how they form, why they rotate plane polarized light, and how to identify them in exam questions. Introduction to optical isomerism in A-level chemistry, A-level specification requirements and key learning outcomes. Optical isomerism describes a situation where two molecules have the same structural formula and bonding arrangement but differ in the way their atoms are arranged in three-dimensional space. These molecules are known as optical isomers or enantiomers. What makes them particularly important is that they interact differently with plane polarized light, a property that can be measured experimentally. Optical isomers are non-superimposable mirror images and arise due to the presence of a chiral center in a molecule. A chiral center is specified as a carbon atom bonded to four different groups, leading to a lack of symmetry. Optical isomers rotate plane polarized light, and that this rotation can be either clockwise or anticlockwise depending on the isomer. Molecules. Racemic mixtures are defined as equimolar mixtures of two enantiomers that show no net optical activity. Definition and identification of chiral centers, structural conditions required for chirality, mirror images, and non-superimposability. Worked example, chirality in 2-chlorobutane. A chiral center is defined as a carbon atom bonded to four different substituents. This specific arrangement leads to asymmetry in the molecule, meaning it cannot be superimposed on its mirror image. For example, in 2-chlorobutane, the second carbon atom is bonded to a hydrogen atom, a chlorine atom, a methyl group, and an ethyl group, all of which are different. This makes the carbon chiral and gives rise to optical isomerism. For a molecule to be chiral and therefore capable of optical isomerism, several structural conditions must be met. First, the molecule must contain at least one tetrahedral carbon atom bonded to four different substituents. This tetrahedral geometry is crucial because it allows for a three-dimensional arrangement that lacks symmetry. Second, the molecule must not possess a plane of symmetry. A plane of symmetry would mean that one half of the molecule is a mirror image of the other, making the overall structure achiral even if individual carbons appear complex. A defining feature of optical isomers is that they exist as non-superimposable mirror images, known as enantiomers. This concept is often compared to human hands, which are mirror images of each other but cannot be perfectly overlaid. In chemistry, two enantiomers have identical chemical properties in most reactions because they have the same bonds and functional groups. However, their three-dimensional arrangements differ, leading to different interactions with plane polarized light and biological systems. The molecule has the molecular formula C4H9Cl and contains a 4-carbon chain with a chlorine atom attached to the second carbon. When analyzing this molecule, the key step is identifying the chiral center. The second carbon atom is bonded to four different groups: a hydrogen atom, a chlorine atom, a methyl group, CH3, and an ethyl group, C2H5. Because all four substituents are different and the carbon is tetrahedral, this carbon is chiral. As a result, 2-chlorobutane exists as a pair of optical isomers that are non-superimposable mirror images of each other. These enantiomers have identical boiling points, melting points, and chemical reactivity in non-chiral environments, but they rotate plane polarized light in opposite directions. One isomer is dextrorotatory and the other is levorotatory. Plane polarized light and its properties, dextrorotatory and levorotatory isomers, the polarimeter, apparatus and function, racemic mixtures, and optical inactivity, graphical representation of light rotation. Plane polarized light is central to understanding how optical isomers are detected and studied. Ordinary light vibrates in all planes perpendicular to the direction of travel, but plane polarized light vibrates in just one plane. This is achieved experimentally by passing light through a polarizing filter, often referred to as a polarizer. Plane polarized light provides a way to observe the effect of molecular asymmetry because optically active substances interact with it in a measurable way. When plane polarized light passes through a sample containing a single enantiomer, the plane of vibration is rotated. This rotation occurs because the chiral molecules interact differently with the electric field of the light depending on their three-dimensional arrangement. Optical isomers are classified based on the direction in which they rotate plane polarized light. A dextrorotatory isomer rotates the plane of polarization clockwise, and this is indicated by a plus sign, plus. A levorotatory isomer rotates the plane anticlockwise and is indicated by a minus sign. It is not possible to predict whether an isomer will be dextrorotatory or levorotatory simply by looking at its structure at this level. Each pair of enantiomers consists of one dextrorotatory and one levorotatory isomer, and they rotate plane polarized light by equal amounts but in opposite directions. A polarimeter is the instrument used to measure the rotation of plane polarized light by an optically active substance. A typical polarimeter consists of a light source, a polarizer to produce plane polarized light, a sample tube containing the optically active substance, and an analyzer to measure the angle of rotation. As plane polarized light passes through the sample, the chiral molecules rotate the plane of polarization. The analyzer is then rotated until the light intensity is minimized or maximized, and the angle of rotation can be read. A racemic mixture is an equimolar mixture of two optical isomers, meaning it contains equal amounts of the dextrorotatory and levorotatory forms of a compound. Although each enantiomer individually rotates plane polarized light, a racemic mixture shows no overall rotation and is therefore optically inactive because the clockwise rotation caused by one enantiomer is exactly cancelled out by the anticlockwise rotation caused by the other. Graphs and charts are often used to represent how the intensity of light changes as the analyzer in a polarimeter is rotated. For example, a graph showing light intensity against angle of rotation can illustrate how the analyzer detects the rotation caused by an optically active substance. Biological importance of optical isomerism, amino acids as chiral molecules, optical isomerism in pharmaceuticals. Optical isomerism is particularly important in biological systems because many biological molecules and processes are chiral. Enzymes, which are biological catalysts, have active sites that are themselves chiral. This means they are often stereospecific and will only interact with one optical isomer of a substrate. As a result, one enantiomer of a molecule may be biologically active while the other has little or no effect. In some cases, the other enantiomer may even be harmful. Amino acids provide an important and relevant example of optical isomerism. With the exception of glycine, all amino acids contain a chiral carbon atom bonded to 4 different groups: an amino group, a carboxyl group, a hydrogen atom, and a variable side chain known as the R group. This makes them optically active and capable of existing as 2 enantiomers. In biological systems, only one optical isomer of each amino acid is used to build proteins, highlighting the importance of chirality in life processes. This selectivity is due to the chiral nature of enzymes involved in protein synthesis. The pharmaceutical industry provides powerful real-world examples of why optical isomerism is important. Many drugs are chiral, and different enantiomers can have very different effects in the body. One enantiomer may be responsible for the desired therapeutic effect, while the other may be less effective or cause unwanted side effects. This is because drug molecules interact with chiral biological receptors and enzymes. Key exam skills for optical isomerism, summary and conceptual overview. Success in exam questions on optical isomerism depends on combining accurate knowledge with strong exam technique. When asked to explain optical activity, students should always link the rotation of plane polarized light to the presence of a chiral center and molecular asymmetry. For racemic mixtures, explanations must explicitly mention equal and opposite rotations cancelling out. Optical isomerism brings together ideas from structural chemistry, three-dimensional molecular shape, and experimental observation. It arises when a molecule contains a chiral center, usually a carbon bonded to 4 different groups. To conclude, optical isomerism is caused by the presence of a chiral carbon atom bonded to 4 different groups. These molecules exist as mirror image pairs called enantiomers, which rotate plane polarized light in opposite directions. Understanding how to identify chiral centers is the key to success in A-level chemistry exam questions. Thank you for watching.